Module 1. Levers. Questions involving levers require the candidate to identify the correct position in which a force must be applied in order to establish the equilibrium between two parts of levers which have opposite tendencies of rotation. In addition, they require one to figure out the missing force at one side of the system to set the equilibrium if the distances from the turning point are given. Another important point of this module is working out the resultant turning effect or moment of force if the equilibrium cannot be established. The situation can be more complex if the weight of the lever is also included in the calculations. In the test, it is very important to approach questions with some urgency as time is extremely limited. One should take care not to linger too long on any single question, as it takes up valuable time which would be better allocated on other more approachable questions. While this guide will explore the means by which to approach the questions regarding levers, it is vital that, if you cannot identify a path to a solution within 10 to 12 seconds, you take an educated guess and move on to the next question. Spending too much time on any single question can cost precious time, which is better spent elsewhere on less challenging problems. First, let's have a quick view on levers before entering into details, which will be discussed when the types of levers are explained. 1.1. What are levers? Levers are one of the simplest types of simple machines. As such, they possess the main properties of simple machines, i.e., they can change the direction of a force, they can change the magnitude of force, and they can change both of the above. Levers consist on a rigid bar which can turn around a fixed point. This turning point is known as a pivot or fulcrum. The turning point divides the system into two main parts. The part that tends to rotate the system anti-clockwise. In the figure, the force F1 exerted perpendicular to the rigid rod at the distance d1 from the pivot tends to rotate the rigid bar anti-clockwise. The part that tends to rotate the system clockwise, in the figure, the force F2 exerted perpendicular to the rigid rod at the distance d2 from the pivot tends to rotate the rigid bar clockwise. Thus, the equilibrium is settled when the turning effects or moments caused by the two forces applied at the given distances from the turning point cancel each other. In simplest words, the condition of equilibrium in this case is total clockwise moment of force is equal to total anticlockwise moment of force. 1.2. Equation of levers. The mathematical equation of the above-mentioned rule is F1 perpendicular times D1 equals F2 perpendicular times D2, where F1 perpendicular and F2 perpendicular are the components of acting forces on both sides of the bar which are perpendicular to the bar length, while D1 and D2 are the distances of the points where the forces act to the fulcrum. In general, a lever is used to lift a load L using a force F. Therefore, instead of writing F1, F2, D1, and D2, we can write L for F1, DL for D1, F for F2, and DL for D2. Hence, the equation of levers becomes L times DL equals F times DF. For example, if the load in the figure below is 20 newtons and the distance of the center of gravity of the load from the turning point is 2 meters, the magnitude of force F will be F equals 20 newtons times 2 meters divided by 4 meters. F equals 10 newtons. 1.3 Mechanical advantage. Another important quantity regarding levers is mechanical advantage, MA. It is calculated by the equation MA equals L divided by F. It calculates how many times easier we can lift a load using the lever than if we simply lifted it using our arms. In our example, the mechanical advantage is MA equals 20 newtons divided by 10 newtons, which equals 2. This means we can lift the load 2 times easier when using the lever instead of carrying it by hand. 1.4 Types of levers. We determine the class of the lever by noting the relative positions of the load, L, pivot, P, and force, F. The 3 possible combinations are pivot located between load and force, load located between pivot and force, force acting between pivot and load. Each of these combinations gives a different class of levers. 1.4.1 First-class levers. A first-class lever is used to lift heavy loads with small forces. It has a fulcrum between the force and the load, as in the figure of the previous example. If the system is in equilibrium, there are 2 equal turning effects, but in opposite directions. According to the law of levers, we can write L times dL equals F times dF. The force applied to the lever can also be calculated from the law of conservation of energy. Look at the figure. Given that work done on the load equals work done by the force, we obtain L times HL equals F times HF. From the similarity of triangles, we obtain DL divided by HL equals DF divided by HF, which equals K, where K is a constant. Hence, we obtain DL equals HL times K and DF equals HF times K. Substituting the last expression in the equation 1, we obtain L times HL times K equals F times HF times K. Simplifying K, we obtain L times HL equals F times HF, which is identical with the equation 2. 1.4.1.1 Examples of first-class levers in daily life. There are many examples in daily life when the principles of first-class levers are applied. Scissors, seesaws, can openers, equal arm balances, and crowbars are all examples of first-class levers. Example: calculate the force needed to pull out a nail using a crowbar as in the figure. The nail can take a maximum force of 2,000 newtons. Solution: a crowbar is a first-class lever, so its fulcrum is, as we see, the distance from the load to the turning point, dl, is 15 centimeters, which equals 0.15 meters. And the distance from the force to the turning point, df, is 1 meter. The maximum force the nail can take, 2,000 newtons, here represents the load, L. Thus, for the force F needed to pull out the nail, we have L times dl equals F times df. 2000 times 0.15 equals F times 1. F equals 2000 times 0.15 divided by 1, which equals 300 newtons. The mechanical advantage of this crowbar is MA equals L divided by F, which equals 2000 newtons divided by 300 newtons, which equals 6.666 infinity. The same result can be obtained also by dividing the distance from the turning point. Thus, from the equation L times dL equals F times dF, we can write MA equals L divided by F equals dF divided by dL equals 1 meter divided by 0.15 meters equals 6.666 infinity. As you can see, the result is the same in both cases. 1.4.2 Second-class levers. A second-class lever has the load between the force and the fulcrum, as shown in the figure. The equation of a second-class lever is the same as for the first-class lever, i.e., L times dL equals F times dF. And the equation of mechanical advantage is also the same. MA equals L divided by F equals dF divided by dL. The only difference here is that in most cases, force distance is equal to the total length of the lever. Wheelbarrows, nutcrackers, and bottle openers are all examples of second-class levers. Take a look at the figures. Example: a man carries a 600 Newton load using a wheelbarrow. What is the force the man applies for the values given in the figure? Find the mechanical advantage of the wheelbarrow. Ignore the weight of the wheelbarrow. Solution. From the figure, we can see that dL equals 40 centimeters, which equals 0.4 meters. dF equals 120 centimeters, which equals 1.2 meters. And L equals 600 newtons. Thus, using the lever's equation, L times dL equals F times dF, we can work out the force F. 600 times 0.4 equals F times 1.2. F equals 600 times 0.4 divided by 1.2, which equals 200 newtons. The mechanical advantage of this wheelbarrow is MA equals L divided by F, which equals 600 newtons divided by 200 newtons, which equals 3. (1.4.3) Third-class levers. A third-class lever has the force between the load and fulcrum, as shown in the figure below. A third-class lever also obeys the law of the lever. L times dL equals F times dF. Sugar tongs, tweezers, forearms, etc. are good examples of third-class levers. Example: calculate the force needed to catch a 20-gram ball using the tweezers as in the figure if the length of tweezers is 9 centimeters and the force is exerted at a point 6 centimeters from the turning point. What can you say about mechanical advantage of these tweezers? Take the approximate value of 10 meters per square second for gravity in this example. Solution. First, we have to work out the load, L, which is equivalent to the weight, W. Given that the mass, M, equals 20 grams, which equals 0.02 kilograms, we obtain L equals W equals M times G equals 0.02 times 10, which equals 0.2 newtons. Now using the equation of levers, L times dL equals F times dF. Substituting the values dL equals d total equals 9 centimeters equals 0.09 meters and dF equals 6 centimeters equals 0.06 meters, we obtain 0.2 times 0.09 equals F times 0.06. F equals 0.2 times 0.09 divided by 0.06 equals 0.3 newtons. The mechanical advantage is MA equals L divided by F, which equals 0.2 newtons divided by 0.3 newtons equals 0.666 infinity. In this case, the mechanical advantage is less than 1. This means the force needed to lift the load is greater than the load itself. For this reason, one may think that this type of lever is useless, as we have to use a greater force than needed to lift the load. However, third-class levers are usually used to lift light objects. Thus, the force is also small. The usefulness of third-class levers consists on the fact that they are used when no other options are available. Ethics is also a reason why we use third-class levers. It is not ethical catching sugar lumps with your fingers. On the other hand, you cannot use your hands to move a burning wooden block, but you can use tongs or tweezers for this. Important note: in all of the above examples, the weight of levers was not mentioned. It is either very small, to be taken in consideration, or it was taken together with the load. (1.5) Finding the correct approach on the questions involving levers. This diagram represents a guide on how to approach the questions about levers. (1.6) Summary. Levers are one of the simplest types of simple machines. As such, they possess the main properties of simple machines, i.e., they can change the direction of a force. They can change the magnitude of force. They can change both of the above. The equilibrium is established when the turning effects, or moments, caused by the two forces applied at the given distances from the turning point, cancel each other. In simplest words, the condition of equilibrium in this case is total clockwise moment of force equals total anticlockwise moment of force. In symbols, L times dL equals F times dF, where L is the load in newtons, F is the force in newtons. dL is the distance from the load to the fulcrum, and dF is the distance from the force to the turning point. The above equation is known as the equation of levers. We determine the class of the lever by noting the relative positions of the load, L, pivot, P, and force, F. The three possible combinations are: the pivot is located between the load and the force, LPF or FPL. First-class levers. Examples of first-class levers include seesaw, can opener, scissors, equal arm balance, crowbar, etc. The load is located between the pivot and the force, PLF or FLP. Second-class levers. Examples of second-class levers include wheelbarrow, can opener, nutcracker, etc. Force acting between pivot and load, PFL or LFP. Third-class levers. Examples of third-class levers include sugar tongs, tweezers, forearm, etc. Mechanical advantage is an important quantity that shows how much easier one can lift a load using the lever rather than carrying it using hands. It is calculated by the equation MA equals L divided by F equals DF divided by DL. In first and second class levers, mechanical advantage is greater than 1, while in the third class levers, mechanical advantage is less than 1. This means that in third class levers, we have to use a greater force than the load. However, they are very useful in certain situations.